Today, in this video, I am going to explain the complete concept of logic gates in a very simple way. In digital electronics, all signals are in the form of binary numbers. That means signals are either 0 or 1. 0 usually represents low voltage, and 1 represents high voltage. Computers, calculators, mobile phones, and many other digital devices work using only these two values, 0 and 1. But the question is, how do we control these signals? How do we decide when a signal should pass and when it should stop? That is where logic gates come in. Think about the gate of your house. If the gate is open, a person can enter. If the gate is closed, no one can enter. In the same way, a logic gate controls whether a digital signal should pass through or not. It takes one or more input signals and gives one output signal based on a certain rule. That rule depends on the type of logic gate. We write that rule in the form of a formula, which is different for different gates. Using that formula, we can also create something called the truth table. First, let us talk about different types of logic gates. There are some basic gates and some advanced gates. The basic gates are AND gate, OR gate, and NOT gate. Then there are special gates like NAND gate and NOR gate, which are called universal gates. There are also exclusive OR gate and exclusive NOR gates. We will study each of them one by one. Let us start with the AND gate. Our AND gate has two or more inputs and one output. The rule of AND gate is very simple. The output will be 1 only if all inputs are 1. If even one input is 0, the output becomes 0. Let us understand this with a real-life example. Imagine two switches connected in series to a bulb. That means the current must pass through both switches. If both switches are on, the bulb will glow. But if any one switch is off, the circuit breaks and the bulb does not glow. This is exactly how AND gate works. Mathematically, if A and B are the variables used to denote the inputs and Y is used to denote the output, then the formula for a two-input AND gate is output Y equals A multiplied by B. In digital logic, multiplication means AND operation. We represent AND operation using this circuit diagram, where these two are the inputs, and this side shows the output. Based on this, let us make the truth table for AND gate with two inputs. Based on the two inputs A and B, where both A and B can take only 0 and 1 as values, we know that we can make a total of only 4 possible combinations. First combination is 0, 0. The second is 0, 1. And third is 1, 0. Fourth is 1, 1. Now apply the rule. If A is 0 and B is 0, then 0 multiplied by 0 equals 0, so output is 0. If A is 0 and B is 1, 0 multiplied by 1 equals 0, so output is 0. If A is 1 and B is 0, 1 multiplied by 0 equals 0, so output is 0. Only when A is 1 and B is 1, 1 multiplied by 1 equals 1, so output is 1. So both intuition and formula give the same truth table. The output will be 1 only if all inputs are 1, otherwise it will be 0. Now suppose there are 3 inputs instead of 2, A, B, and C. Whenever the number of inputs increases, the total number of possible combinations also increases. The total combinations can be found using a simple rule, 2 to the power of the number of inputs. Since each input can be either 0 or 1, for 3 inputs we get 2 to the power 3, which is 8 different combinations. We write the 8 combinations like this. There is also a shortcut way to quickly make the truth table without writing random combinations. For 3 inputs, write 8 rows. Then fill the first input column for A by writing 4 zeros followed by 4 ones. For the second input column, write 2 zeros, 2 ones, then 2 zeros followed by 2 ones. For the third input column, write 0, 1, 0, 1, and so on. This systematic method ensures that all 8 combinations are covered correctly, without missing any case. After filling the input columns, simply apply the gate rule to each row to find the output column. In equation form, for 3 inputs, we write output Y equals A multiplied by B multiplied by C, and the circuit diagram looks like this. Now, if you multiply the row values one by one, in a 3-input AND gate, the rule remains the same. The output is 1 only when all inputs are 1. So only the last combination, 1, 1, 1, gives output 1. All other 7 combinations give output 0. Once this is clear, the rest of the logic gates will become easy to follow. Next, let us understand OR gate OR gate also has two or more inputs and one output. In OR gate, if at least one input is 1, the output becomes 1. The output is 0 only when all inputs are 0. Let us take a real-life example. Imagine two switches connected in parallel to a bulb. That means if any one switch is on, current can flow, and the bulb will glow. Only when both switches are off, the bulb will not glow. The formula for a two-input OR gate is output Y equals A plus B, and this is the circuit diagram. Now let us write the truth table for two-input OR gate. The four combinations are these. Remember the shortcut to make them. 0, 0, then 1, 1 for the first column, and 0, 1, 0, 1 for the second column. Now apply the rule. If both are 0, output is 0. In 0, 1, 1 is present, so output is 1. In 1, 0, again 1 is present, so the output is 1. In 1, 1, output is also 1, so only 0, 0 gives 0. All other cases give 1. If there are three inputs, the output becomes A plus B plus C. Even if one of them is 1, output becomes 1. Only when all are 0, output becomes 0. Now let us understand NOT gate. NOT gate is very simple. It has only one input and one output. It just gives the opposite value. The truth table has only two rows. Input 0 gives output 1. Input 1 gives output 0. In equation form, we can write output Y equals A with a bar, which means opposite of A. Next, we move to NAND gate. NAND gate is made by combining AND gate and NOT gate. The rule is simple. We first perform the AND operation. Then the result we get from AND operation is inverted using NOT. That is why the name is NAND, which means not AND. In AND gate, only when both inputs are 1, output is 1. But in the NAND gate, when both inputs are 1, output becomes 0. In all other cases, output becomes 1. This is its circuit diagram. We get this D shape from AND and this circle from NOT. So its formula will be this, and the truth table for two-input NAND gate is super simple now. So only 1, 1 gives 0. All other cases give 1. The same thing can be done for three-input case. Now the NAND gate is called a universal gate because we can build AND, OR, and NOT gates using only NAND gates. That means with only NAND gates, we can create any logical circuit. Next, let us understand NOR gate. NOR gate is made by combining OR gate and NOT gate. First perform OR operation, then invert the result. So NOR means not OR. It is just the opposite of OR gate. In the OR gate, if any input is 1, then the output is 1. But in NOR gate, if any input is 1, output becomes 0. Only when all inputs are 0, output becomes 1. So its formula will be this, and its truth table will look like this, right? Easy peasy. NOR gate is also a universal gate, because we can build all other gates using only NOR gates. Now, let us talk about exclusive OR gate, also called XOR gate. In XOR gate, output is 1 only when inputs are different. If both inputs are the same, output becomes 0. Let us check the truth table for two inputs. For the first row, we have 0, 0, which means both inputs are the same, and thus the output becomes 0. For the second row, we have 0, 1, which means both inputs are different, and thus the output becomes 1. Similarly, 1, 0 gives 1, and 1, 1 gives 0. In equation form, XOR can be written as A times B bar plus A bar times B. This is the circuit diagram of this gate. Now here is the fun part. We can also design the circuit diagram of the XOR gate using basic gates like AND gate, OR, and NOT. Use this formula to design the same. Look here, we first take input A and input B. Then we pass B through a NOT gate to get B bar, and pass A through another NOT gate to get this A bar. After that, we create two AND operations. The first AND takes A and B bar, or this term. The second AND gate takes A bar and B to get this term. Now here we have a plus sign, right? So finally we connect the outputs of these two AND gates into one OR gate. The output of that OR gate becomes the final output of the XOR gate. That was super cool. Now if you want to think about what this gate does intuitively, it simply checks for inequality between inputs. If two inputs are not equal, we get 1, else 0. Finally, we have exclusive NOR gate, also called XNOR gate. This is the opposite of XOR gate. In XNOR gate, output is 1 when inputs are the same. If inputs are different, output is 0. So 0, 0 gives 1. 1, 1 also gives 1. 0, 1 and 1, 0 gives 0. Its formula can be given as Y equals AB plus A bar times B bar. Now take pen and paper and try to draw the circuit diagram of this gate using basic gates, and let me know in the comments how you did it. Like, share, and subscribe.